So, hello all. In today's sessions, we'll discuss how to calculate safe load, how to calculate slenderness ratio, and if factor of safety is given, how to find out that safe load for various conditions that we'll discuss. Okay. Now, suppose say the statement is calculate the safe and compressive load on hollow that material is given. Column with one end is rigidly fixed and other is hinged. The column having 120 mm external diameter, 100 mm internal diameter, and 10-meter length. Use Euler equation with factor of safety 5. Take elasticity 95 into 10 raised to 3 Newton per mm square. Okay. Now this statement is available. Now what we have, hollow column is given, so we can take area is equal to pi by 4 OD square minus ID square. Now what is outer diameter? 150 mm. What is internal diameter? 100 mm. So you can get that area pi by 4 150 square minus 100 square, that is 9817.47 mm square. Now what we have area moment of inertia pi by 64 d raised to 4. Now again instead of d raised to 4 we can write 150 raised to 4 minus 100 raised to 4. So we'll get that value of I, that is 19.9417 into 10 raised to 6 mm raised to 4. So first we'll find out area and moment of inertia. Now we'll apply that condition. They have asked to calculate that safe load when both the ends are P. That means equivalent length is equal to L by root 2. So we have that equation P is equal to pi square EI upon LE square. We'll replace L is equal to L by root 2. So that equation will become 2 pi square EI upon L square. So put that value of E, that is 95 into 10 raised to 3 Newton per mm square. That elasticity value is available. Take that value of I, 19.94 into 10 raised to 6 mm raised to 4. And we have length, that equivalent length is 110 meter. So that is, that value we have taken, that 10 meter into 1000, that is 10,000 mm bracket square. So if you put all these values, then you will get that buckling load, which is 373.95 into 10 raised to 3 Newton. Now we have factor of safety, which is 5. So what will be the compressive load, safest compressive load? Buckling load upon factor of safety, that is 373.95 into 10 raised to 3 upon 5. So you get that safe compressive load 74.79 kilonewton. Okay. Now, second problem. Suppose if you want to calculate slenderness ratio. So the statement is calculate the maximum value of slenderness ratio of mild steel column for which Euler formula is valid. Take elasticity 210 megapascal and that crippling stress is given 330 Newton per mm square. Now what we have discussed in earlier session, we have Euler's equation pi square EI upon LE square. Okay. Now by assuming both the ends are hinged, we can write LE is equal to L. So what is that equation? Pi square EI upon LE square is equal to, just replace that I value. I is equal to AK square, moment of inertia. And we have LE value. So we can take that LE is equal to L. Okay. So what we have P by A, that is P by A is equal to pi square E upon L by K bracket square. Okay. Now that LE we have replaced by L. So finally we will get force upon area, that is crippling stress is equal to pi square E upon L by K bracket square. And this L by K is nothing but your slenderness ratio. So you can write L by K bracket square is equal to pi square E upon crippling stress. Okay. So L by K is equal to under root of pi square E upon crippling stress. So finally we can take that pi outside that bracket. So L by K is equal to pi into under root of elasticity upon crippling stress. Now we have that value of elasticity 210 GPa, that is 200 into 10 into 10 raised to 3 MPa, and stress is available 330. So if you put that elasticity and stress, you will get slenderness ratio L by K, which is 79.250. Okay. So in this way, we can calculate slenderness ratio. Now to get that slenderness ratio, first we have to determine that equation for slenderness ratio. And to get that equations, we have apply that equation of buckling load. P is equal to pi square EI upon LE square. Just we have replaced L is equal to L and I is equal to AK square. So we get that slenderness ratio. Okay. Next part, suppose if you want to calculate safest load. Now again, suppose this is the one statement. They have given solid circular bar with 25 meter length and 120 mm diameter, which was found to extend 1.2 mm. That is, deflection is given under the tensile load of 52 kilonewton. The bar is used as a strut to determine crippling load and also safe load by taking factor of safety 3 with following condition. So they have given this condition, both the ends are fixed, one end is fixed, other is hinged, and third part they have given both the ends are pin joint. So first we have to determine the value of elasticity. Now what is area of that shaft? Pi by 4 d square, pi by 4 120 square, that is for solid circular bar. Then delta deflection is PL upon AE. So what will be the E value? Elasticity is PL upon area into deflection. Now force is given, tensile load is given 52 kilonewton. Length is given 25 into 10 raised to 3, that is in mm. Then we have area pi by 4 d square, pi by 4 into 120 square, and delta L is given 1.2 mm. Okay. So if we put all these values, then you will get elasticity. It will be 95.79 into 10 raised to 3 Newton per mm square. Now we will apply that conditions. First is both the ends are fixed. So we have equivalent length is equal to half of actual length. Okay. So we put that L is equal to L by 2, then you will get equivalent length 12500. Okay. So we can apply that crippling load, equation of crippling load, pi square EI upon L square. We have elasticity value 95.79 into 10 raised to 3. Then we have I value, okay, that I value is pi by 64 d raised to 4. That is pi by 64 120 raised to 4 upon L 12500 square. So if you put all these values, then you will get P crippling load 61.59 kilonewton. And the safest load will be crippling load upon factor of safety. That is 61.59 upon 3, which will be 20.53 kilonewton. Now second condition is, suppose say one end is fixed and other is hinged. At that time, equivalent length is equal to L by root 2. Okay. So if we apply that equivalent length L by root 2, then we have 25 into 10 raised to 3 upon root 2. So you can put that value of P is equal to pi square EI upon L square. So we have E value, we have I value, elasticity is available, moment of inertia is available. So you get that crippling load 30.79 kilonewton, and safest load will be force upon factor of safety. This crippling load upon factor of safety, which is 10.265 kilonewton. Okay. And third conditions we have, if both the ends are pin joint, at that time equivalent length is equal to actual length. So we'll get that crippling load pi square EI upon L square. That load will be 15.4 kilonewton, and safest load will be crippling load upon factor of safety, that is 15.4 upon 3, that is 5.13 kilonewton. So in this way, when the deflection is available at that time, we have to find out elasticity, because modulus of elasticity is not given in this problem. So first we have calculated that E value, modulus of elasticity, and then we have calculated that crippling load and safest load. Thank you all.